Today I'm going to talk about my research in ion trapping and then go over, what are the different marvelous things you can do with ion traps. And I hope that by the end of the talk, I can convince you guys that it's indeed marvelous. All right, let me do the slideshow. You can still see it, right?
Yeah, it's not a full screen. I can see multiple windows.
Is it not showing the full screen? Play from, okay, I guess I can just do it like this. So basically, I'll go over why do we care about ion traps? What are they? And then when I talk about ions, the main focus today is going to be highly charged ions because I've worked mostly with highly charged ions during my PhD work. And then I'll go over different application of ion traps. But just to give you guys an idea of why we are interested in ions, you can see this map where you can see that basically our universe is made of more than 95% of ions. And at Earth itself, there's less than 0.1% ions. So if we want to learn about the universe and different phenomena that's occurring, then we want to be able to study these ions and we want to be able to produce them and trap them. And this is what we use ion traps for. So give me a second. I'll try to this. Okay. So here I'm showing you the different pioneers of ion trapping and cooling trapped ions. So you can see beginning in 1984, there has been multiple Nobel Prizes awarded in the research. And as I go over the talk, you'll realize how all the work done by these pioneers have contributed in making our understanding of ions and controlling things in a better way. So how does an ion trap work? So basically what we are trying to do in an ion trap is we are trying to store charged particles and we mostly work with positive ions. So we are working with positively charged ions. And one of the early limitations before the development of ion traps was that to trap anything in 3 dimensions, you cannot just do it by applying purely electrostatic potentials. And this is actually a mathematical expression that you can go over given by Earnshaw. So if you want to trap ions in 3 dimensions, then you have to come up with a solution to do that. And there were actually around the same times 2 different solutions proposed. One of the solution is that you can trap the ions in 2 dimensions by applying the electrostatic potentials, but on the 3rd dimension, you can add a magnetic field. And if you remember the motion of the charged particle in a magnetic field, it will be perpendicular to the magnetic field and it will induce a centripetal force basically that confines the ion in this circular motion. So this is how the application of larger magnetic field can trap the ion in this direction. And then in this direction, basically in the axial direction, you can trap them by just applying a electrostatic potential difference between these 2 end caps, and in the radial direction you can trap them by applying the magnetic field. So this is one way, and these kinds of traps are called penning traps. Now there is another kind of traps which are called Paul trap or RF, meaning radio frequency. And the idea here is that so you'll apply not only the DC potential, but you provide a alternating potential in between these 2 end caps and the middle electrode, which we call a ring electrode, which is this hyperbolic shape shown here. And the reason you want to do that is that the shape of the potential is quadratic. So it looks like a saddle, basically something like this. And as you can see that there is if you try to trap in one direction, then you won't be able to trap it in the other direction. And it's similar on the other side as well. So the idea which is shown very nicely in this demonstration of a mechanical rotating saddle, is that, just take a look at it. So right now we have not applied any rotating force. So the ball wouldn't be trapped or stick to the saddle, but now we are adding a rotation to this system. So basically now when you add the ball or add your ion in this hyperbolic or this quadratic potential, then you can end up trapping them because you are oscillating in between the two shapes that's shown in the upper right here. And you just have to make sure that you're applying a frequency that's just larger than the oscillation frequency of the ion itself. So this is how trapping actually occurs in these two traps. Just to go over highly charged ions. So highly charged ions, as you know, just if you think about an ion, is something where an electron is removed from the atom, so that's how it gets ionized. Now, if you think about heavier atoms, which have many electrons, and you are basically removing a large number of electrons from these systems, then you create what's called an highly charged ions. And the interesting thing about them is if you look at this chart, the highly charged ions are present in solar atmosphere, in different galaxies, supernova and fusion plasmas and all that. And the temperature is usually quite high. So these are very, very hot, 10 to the 5 Kelvin, and the density of the charged particles is also quite large. So we want to be able to create a atmosphere in our lab that's quite similar to this if we want to study these ions, right? And the other reason why highly charged ions are interesting is that they behave quite different from neutral atoms. For example, if you look at this cartoon here, it shows a comparison of a hydrogen atom versus a hydrogen-like nickel ion. So if you think about this, nickel has 28 electrons. So what hydrogen-like means is that you have removed 27 electrons from the system. So it only has one electron remaining, and that's why it's called hydrogen-like, but it's still a nickel atom. But in the process of removing electrons, what happens is that the spatial electronic wave functions becomes quite compressed, and the size of the atom now becomes much more smaller than the neutral atom. And what this does is that the electronic orbitals, they start overlapping with the nucleus because they are so close to the nucleus right now, right? So this allows us to not only study about the atomic physics and the electrons, but it also allows us to probe the nucleus itself, so dig into the nuclear physics realm, which is quite exciting. And then the other thing with these highly charged ions are how the photon energy scale. Z here is the nuclear charge, and you can see that the energy splittings in this system scale with the 4th power of Z. What this means is that a normal transition that would produce photons in the visible region for neutral atoms is now shifted to the X-ray region. So anytime, let's say, one of the NASA X-ray telescopes captures some features, they might be very likely coming from highly charged ions from whatever they were measuring or observing. The other thing that's exciting about highly charged ions are their strong relativistic effects. So as you can see, electrons in highly charged ions travel nearly at the speed of light. And then they also experience extreme electric fields due to their high charge, which is shown by this equation right here. Now, if you think about the relativistic property of something that has a large atomic number, for example, gold, have you ever wondered why the color of gold is yellow? It's actually because of its relativistic property. What happens is that the electrons, they are moving so fast that they experience relativistic contraction, and the light of the radiation that's absorbed by these elements is shifted towards blue. So what it does, it basically absorbs all the blue light and it reflects all the yellow light. And that's why we see gold as yellow in color. So now imagine that you make these systems highly charged, the effect just amplifies by quite a bit. So that's something really exciting about highly charged ions. Now, the thing is that we want to be able to produce them. And one way to do that is in these large accelerator facilities. For example, the one shown in the right is a storage ring where they do production and measurement of highly charged ions. If you want to know what a particle accelerator is, it's basically a large circular device where there are application of electric and magnetic field to confine the charged particle. And each time the charged particle rotates in this circle, it just accelerates and the energy becomes quite large. So you can think of it as a car in a racetrack. So you cannot just start with a very high acceleration right in the beginning, but as you go through the circle, you are just increasing your speed by quite a bit. So this is what is done in a storage ring as well. The other place where these highly charged ions and these hot plasmas are created are devices that are called tokamaks. And it is basically just a system, a large vacuum chamber that has lots of magnetic coils. And then the idea is that you create a plasma that's created by fusion inside, and then you apply this magnetic field to confine the plasma inside this device. And there are many tokamaks around the world, but one of the very interesting one that's been in construction for a while now is the one called ITER. So if you go to this website, you can learn all about what ITER is, but basically it is a largest tokamak that's being built to be able to be used as a fusion power plant. And it's a collaboration among 37 countries. Their idea is that by doing fusion with the two isotopes of hydrogen and trapping them in this device, you just create an enormous amount of heat and use that heat in order to convert it into electricity. So these are the large devices that we have around. But as we know, these are quite expensive and these are not so accessible. So we want to be able to have a system that can create and trap these highly charged ions, but more in a laboratory scale so that we can do these experiments within our universities, right? So where else can we do this? We can do this in what's called an electron beam ion trap. So this picture is actually during my PhD, and this lab is in the National Institute of Standards and Technology. It's the Ebit lab. And so just to give you an idea of the electron beam ion trap, it's, if you remember in the beginning, I talked about two kinds of traps, penning trap and ball trap. So an electron beam ion trap is basically a type of penning trap such that you have several electrodes and you're applying an electric field in between these electrodes to trap them in the axial direction. But then you also have a large superconducting magnet, which will help you trap it in the third dimension in the radial direction. The only addition here is because we want to be able to create highly charged ions, we also need an intense electron beam. So these electron beams will then enter the trap, and then they will collide with the atoms that are in the trap. And then they will strip the electrons out of the atom and make it more ionized. And depending on the energy of these electrons, you can decide how much ionized you are getting, right? So give you an idea of what actually happens. There's a nice representation video that I like to show. So as I said, there are a bunch of electrodes, and then you inject the electron beam from one end, and the electron beam basically helps you to create, trap, and study the highly charged ions. So what happens inside the trap itself is you're injecting very high energy electron beam, which interacts with a neutral atom. And then in doing so, it removes the electrons from the atom. And that's how it creates a positively charged ion. And the more energy the electron beam has, the more electrons are removed from the system. So basically, the advantage is also that the positive ion is now attracted to this negatively charged electron beam, and this helps further in the trapping of the ion inside the trap dimensions. Now, what happens is further collisions can occur depending on the energy of the beam. And when this happens, the electrons get excited to a higher energy level. We know that whenever something excites to a higher energy level, it has to come back to the ground state by emitting photons. And these photons are what we are going after. So we are basically looking at the spectrum or the radiation that's emitted by this Ebit plasma. And by studying these photons, by measuring these photons, we can actually do research of the system that mimics similar condition as in solar flares and fusion reactors. So what's special about an Ebit? So I told you that we can create highly charged states, and the plasma emits radiation, and these radiations can be in different wavelength region. So this is a picture of the NIST Ebit, and what I'm showing here is basically this is the trap. This is where the trap is, and you can see that there are many output ports. So based on what kind of wavelength you are interested, you can just install different detectors and spectrometers to measure the radiation. And in addition, you can also not only look at the trap and do spectroscopy, but you can also extract these ions and then send it for other experiments, right? So just to remind you, the conditions inside the Ebit are much similar to what's shown in this plot. The temperatures are around 10 to the 5 Kelvin, and the density is around 10 to the 13 particles per meter cube. One of the things we have to be mindful about when talking about these ion traps is that they work in ultra high vacuum conditions. And we want this because there are so many charged particles of different polarities. So there are collisions that occur, and these collisions sometimes result in ion losses. And then on top of that, if you are doing this in air condition, then you have extra gases in the system that will just result in more collisions, and in the end, result in difficulty in trapping the ions of interest. So we need to be able to trap them, and for this, we have to have a vacuum of around 10 to the minus 9 millibar. Which if you compare it with atmospheric pressure, it is a 10 to the 9 smaller than the atmospheric pressure. And the other thing we have to also do is, because the magnet we use in these systems are superconducting, we have to cool them down to liquid helium temperature, which is 4 Kelvin. Coming back to why do we want to use Ebit for spectroscopy, I like to show this plot. This triangle is basically showing you the atomic number in your x-axis, and then the charge state, in the y-axis, and the charge state in your x-axis. And the color code is basically telling you that the dark blue is where there is no data available. And then as you go from these different colors, then there is more and more data available. So you can see that there's this huge gap, huge section where there's no data. And this creates difficulty among researchers from different communities, like the astrophysical communities or the fusion communities, or even theorists who are doing atomic calculations. So it shows you that there is this huge need of being able to measure these atomic data and then fill in the gap. How do we do that? We do that by using spectrometers. So if you need to remember about how spectrometers work or what spectroscopy is, you're basically just measuring the emitted spectra that results from the interaction of light with matter. Now, for example, if you look at this plot, you just have a white light passing through a prism, and then that just disperses into multiple colors. So something similar happens in spectrometers as well, where you have a source, and then you send the light to a mirror. The mirror is basically used to focus the light and to collimate them. And then you send it to some kind of grating element, depending on what wavelength you are trying to measure. And then the grating makes sure that the light is dispersed, and then the dispersed light is collected with different kinds of detector. Just a reminder, the wavelength, the shorter wavelengths are in the gamma rays, and as you move to the right, you shift from gamma to X-rays to ultraviolet to visible, and so on. So what I did during my PhD was most of the work was done in the extreme ultraviolet vision, which is in this wavelength. It's around 1 to 40 nanometer. And this is the setup that's shown there, which is connected to, so this is where the electron beam ion trap is, and the spectrometer is connected to one of the output port there. Like I showed you how a spectrometer works, you basically need a source, light source. In this case, the light source is the Ebit plasma. And then you need a mirror. So we used a large spherical mirror to be able to collect as much light as we could. And then that was sent through, there is a slit in here. So the slit basically collimates the light, and then you send it to a grating element. So in this case, there's a reflection grating, and then that's sent to a CCD camera, which is similar to the cameras that you can find in your phones. A typical extreme ultraviolet spectra that is collected looks something like this in the black. So here, what I'm showing you is a extreme ultraviolet spectra that was collected for yttrium at an experimental energy. So this energy is corresponding to the kinetic energy of the electrons. So remember, depending on the kinetic energy of the electrons, we can create specific charge states of any elements, right? So in this case, we had around 5 kilo electron volts, and we were creating different kinds of ions, lithium-like, beryllium-like, carbon-like, and so on. So lithium-like is where all the electrons are removed except 3. Beryllium, you have 4 remaining, and so on. And this is showing a comparison between the experiment and theory. And you can see how nice the theory is as well. And all it does is it looks at all the collisions that happens inside a Ebit-like system, and then it does the atomic calculations for this particular system. One of the things I want to point out is that if you look at the blue plot versus the black one, you can see that these lines are actually not present in the experiment, in the theoretical spectra, right? And the reason is that if you remember, the grating that we used was actually a diffraction grating. So basically what we are seeing here is the second order of these transitions. And then we are also seeing some of the third order of the same transitions. So that's the beauty of using a diffraction grating, and that helps you identify the transition in much more accurate ways as well. And if you're wondering why only certain charge states are created, like why do not we see a helium-like or a hydrogen-like? The reason is that for a helium-like, it's a closed shell, so it's much more bound to the atom. So you just need much larger energy to be able to knock one more electron out of the system. That's why we see barium-like, lithium-like, but not helium-like. So why do we use these spectra? So there are multiple applications. One of the applications is, like I pointed out, similar conditions, similar plasma are available in different kinds of fusion plasmas. And I also mentioned about ITER, which is basically a fusion power plant that's being developed. And one of the things with ITER is one of the element in the chamber is made of tungsten. So in these high temperature conditions, what can happen is that these tungsten gets highly ionized. So you end up getting not only your fusion elements in the trap in your plasma, but you can also get impurities from this tungsten. So we wanted to learn how this tungsten affects the fusion plasma. And then the other thing we also wanted to do is that even though this is impurity that can potentially create problem in the fusion plasma, you can also use these as a diagnostic element. So basically, once you have all the information about the transitions that can happen in these charged states of tungsten, you can then use this information to determine the temperature, the number density, and other parameters of the plasma, because there is no easy way to just probe the temperature by inserting something inside the plasma, right? It's so hot. So that's one of the advantages that you can use these transitions for. We did similar studies for yttrium, one of the spectra I showed you earlier. Basically, it's the same idea, but for this application, the fusion tokamaks that we were looking at were different ones. Now, the other application of doing UV spectroscopy is to study about nucleus. Like I mentioned in the beginning, the size of the electron cloud gets much more closer to the nucleus in highly charged ions, right? So because of this, there is a huge overlap of this is not a very good representation, but there is a huge overlap between the nucleus and the electron cloud. So what we did is we basically measured these atomic transitions between the electrons of such system. And by using these transitions, we were actually able to extract the nuclear size of some of the elements. And this was one of the first measurements done in the EUV region with this idea. And we were able to measure the difference in the nuclear size of two xenon isotopes. And we have done other experiments with heavier isotopes that we are currently analyzing. But this is a great way to be able to measure the nuclear size of some of the isotopes that we do not have any nuclear data available for. For example, we can do similar tests in the radioactive beam facilities where all the heavy radioactive isotopes are present by applying a similar technique. What else you can do? You can also do spectroscopy in other wavelength regions. So in addition to the EUV spectrometer that I showed you earlier, and I pointed out that there are multiple output ports in the Ebit. So what that does is that we have access to all kinds of spectrometers. And so as a result, we have spectroscopy in the X-ray region available as well. And this is just showing you two X-ray detectors. And the idea is same. The spectrometer works on exactly similar functioning as I described before. The only thing that's different is that to be able to measure the wavelength of interest, you have to make sure that the d-spacing is comparable to your lambda. So if you remember your diffraction equation. So this is why we mostly use crystals with a very small lattice spacing for X-ray region, because X-ray region has much smaller wavelength than the region that we were exploring earlier. So some of the applications of the X-ray spectroscopy with Ebit comes more in the astrophysics applications. So for example, this was a study we did when there was this paper where they basically talked about one of the unknown X-ray feature that was found in a spectrum of galaxy clusters that was imaged by the XMM neutron spacecraft. So, whenever there is something unknown and unique that shows up in a spectra, everyone is excited that it's something from dark matter. So this paper actually created a huge wave of different kind of follow-up research because everyone wanted to find out what it's coming from. And one of the things that they had pointed in this paper is that So whenever you look for the spectra that's available in the atomic database to compare to what we are observing, you have to rely on the atomic models, and astronomers usually use the database called AtomDB, and this one it includes most of the atomic processes, but one of the processes that they do not have data for is what's called a dielectronic recombination process. Because this is a resonant process, it only occurs every now and then, but it is very, very strong. So the paper had pointed out that it might be likely coming from this transition, this process in argon, and this is exactly what we measured. So we did some observation of the argon dielectronic recombination lines, and what we found was that although this did not cover or explain the complete unknown feature, it did contribute to some of it. So this unknown thing was actually coming from the unknown atomic processes in the available atomic models. So this is why we want to be able to do all kinds of spectroscopy and add as many atomic data as possible in the database. So something similar in the infrared region that I'm interested to do is motivated by the upcoming James Webb Space Telescope. So this telescope will be mainly observing features in the infrared region. So we want to be able to use Ebits or other ion traps in the infrared region, because there hasn't been many measurements in the infrared region, and there's a huge data gap in this region. And we do have the proper spectrometer that can measure transitions in this region, and using both the NIST Ebit and also the RF trap that's here at App State. I am interested to measure transitions in the infrared region for different kind of elements such as iron and argon that's most dominant in the astrophysical plasmas. All right, so far I talked about why spectroscopy with ions is important. It's relevant to cosmology, fusion research, R&D, understanding about atomic structure, atomic theory, metrology. I'll briefly talk about medicine later. But what other applications of ion traps are out there, and what are they being used for? So the next few slides, I'll go over that. One of the things that ion traps can be used for is also to measure the nuclear masses. Now, why do we care about nuclear masses? There are two different reasons. First of all, we want to be able to understand the structure of the nucleus, and the nuclear models, the nuclear shell model still has many things that needs to be figured out. And these are mostly associated with heavier radioactive isotopes. So the more number of measurements you do for these masses, you'll actually realize that new features are being discovered, and the theory has to be adjusted accordingly. The other thing is related to nuclear astrophysics. So if you look at the very famous Einstein's equation, E is equal to mc square. It's basically telling you that even for a tiny amount of mass, because of this huge proportionality constant, it results in an enormous amount of energy. And this equation actually tells you how fast a nuclear reaction can occur, and what was the origin of a certain reaction, when it occurred, how it occurred, and things like that. So by measuring the mass, which is one of the parameters you want to use in your nuclear reaction rates, you can actually learn a lot about situations that happened in the early universe, some of them shown in this picture in the right. So here I'm going to talk about some of the work I did as a postdoc at TRIUMPH, which is a Canadian particle accelerator facility. Just to give you an idea of where TRIUMPH is, it's in Vancouver, right at the border of US to Seattle. And TRIUMPH is basically a cyclotron-based facility. So a cyclotron is used to produce very strong protons. The protons then hit to some kind of target, and different radioactive isotopes are created in the process. And then the radioactive isotopes are then sent to the experiment hall, where there are many different experiments going on. And then the one that's circled out here is basically where I worked at. So this facility is a set of ion trapping facility. It's called Titan. And just looking from this end, the one on the top is actually where the ion trap facility is located. And all these features are just showing you the beam lines and vacuum chambers where the radioactive beam is transported from. So just to give you an idea of TRIMS ion trap, so in addition to the electron beam ion trap that I discussed about, there are so many more ion traps, which is the exciting thing. So what happens, just a brief overview, is that you get your radioactive beam, you send it to a radio frequency quadrupole trap where it's cooled. You then can send it to this other trap, which I'm not going to talk about, but then you can send it to the mass measurement penning trap where all the nuclear mass measurements happen. And you can either send singly charged ions to this trap for mass measurements, or you can send it to an electron beam ion trap, and then you can increase the charge state of this species and then send it back to the mass measurement trap for measuring the masses. So just coming back to how masses are measured in a penning trap, you remember this layout from before. It's the same idea. You have magnetic field, you have electric field, you can find the ions. And this time what you're looking for is it's basically how fast the ion is spinning. So you measure the cyclotron frequency of this ion, which is dependent on the charge over mass ratio and the magnetic field. Now, the charge and the magnetic field is a fixed number for a particular ion. So when we measure the cyclotron frequency, we can then extract the mass of the ion, which is how we do mass measurements. So now the application of an electron beam ion trap is also relevant to the measurement of masses, because you can increase the mass measurement precision if you use highly charged ions. This is because the mass measurement precision scales with the charge state. So the higher the charge state, the better the precision. This is a unique system where you can do this, where you can charge braid your ions and then send it back to the mass measurement penning trap for mass measurements. The other really exciting things that ion traps are being used for, I like to show this picture, which is a schematic of one of the trapping facility in Germany. So you can see that there are multiple traps being used. So on the left, there is your electron beam ion trap, which is basically used for highly charged production, but these highly charged ions are quite hot and energetic, so you want to be able to cool them down. And to do that, you send it through another device, and then in the end, you send it to a ball trap, which I also talked about in the beginning. So now in the ball trap, which has access to optical pores where lasers can be also inserted, what you can do is you can cool these ions. And researchers have been able to cool ions to nearly absolute zero millikelvin temperatures. So what this does is that the ions become so slow that you can basically control the quantum state of the ion, and you can even change the nature of the material, basically forming what's called a Coulomb crystal, where the thermal energy of this ion is so much more than the Coulomb energy. And then the other thing that's because of this ability to be able to control them so precisely is using the ions or ion traps as quantum computers, or as qubits for quantum computers. And you can do more research on this. I like this website, ionq.com, which goes through how quantum computers work and how they use ion traps for quantum computing. But basically, this is a very ongoing research where they're trying to trap multiple ions to be able to use multiple bits in the quantum computers. And just like the regular bits 0 and 1 in your regular computers, the difference now is going to be that there's going to be different quantum states, and the superposition of these quantum states will give access to not just 2 bits, 0 and 1, but a superposition of these bits, making the computational speed quite fast. So a few other things, just quickly to point out. As I mentioned, we can do atomic spectroscopy. You can measure the masses that's inside the trap. But what we can also do is we can extract these ions for different kind of studies. And one of such studies that we do at the Clemson electron beam ion trap is that you take these energetic ions and then you interact it with different kinds of surface of different kinds of materials, even in the nanoscale. And then by using this technology, you can do an implantation, you can do nanolithography, and all cool surface science studies. There's also been interest in using such devices for particle therapy. And the reason is that charged particles, since they can be focused by electric and magnetic fields, it just gives us the freedom to be able to scan the ion beam over tumor cells very precisely. And if you look at, for example, proton therapy, if you look at protons, you can see that the dose versus depth is showing that most of the energy is deposited at the end, which means that maximum energy deposition is actually occurs in the tumor cells itself and not on the other cells when the particle is moving through your body. So there's also some interest in figuring out how to use charged particles and also highly charged ions to be able to use them for particle therapy. And to end with, just like to briefly talk about room temperature Ebits. So the ones that I was talking to you about was in ultra high vacuum, and they have these large superconducting magnet, which kind of prohibits the use of lasers in the optical center region, and these are also comparatively expensive. So as an alternative, the very latest developments has been and is still being conducted in building this even smaller electron beam ion traps, which are called compact, and there's been like several built already throughout the world. So the basic working is the same. The only difference is that instead of superconducting magnets, you're going to be able to use permanent magnets, and then these center trapping region will also have optical access to laser, so you can control the ions, you can cool them, you can manipulate them. So this is something exciting, and this is something that I am also interested to do in the recent future. Just would like to thank my collaborators, and thank you all for listening to this talk. And I welcome any questions.
Thank you for your talk, Dr. Silwal. I think Anton has a question. You can go ahead. Can you hear me, Anton?
Yeah, I can hear you.
Okay, good.
So it was not a question, it was just a clap. So, but I can ask some question. Let me think. Could you so your talk was about like large facilities, right, where you can get this, get and store this type of atoms. And could you explain in more detail which facilities do we have in upstate so that you can continue your research here?
Yes, so basically at Upstate, we have, let me go to the very beginning. So I showed you two kinds of traps. At Upstate, we have one of the RF traps. Dr. Anthony Calamai's lab has the radio frequency trap, and it's quite similar to this schematic. The only difference is that instead of a hyperbolic shape, it has a cylindrical shape. And yeah, you are able to do trap ions, and usually it also has electron gun, and you can create low charged ions in this particular trap. My ultimate goal is, of course, to be able to write and get a grant to be able to build an electron beam ion trap, because that's my real interest. But we can do very similar studies with the RF trap itself. And one of the things that I pointed out earlier is to be able to do spectroscopy in the IR visible region, which is very, very good with the ion trap and its capabilities right now.
And for this electron beam, how many electrons can you remove from the atom to get solid?
So you can, as long as your electron beam kinetic energy is large enough, in the 50 kilo electron volt range, you can basically create pretty much any charge state. So at the NIST Ebit, we've been able to create hydrogen-like, helium-like, heavier stuff. At the Livermore Ebit, they have been able to create hydrogen-like uranium, which needs, I have to look the ionization energy to be able to tell you exactly what, but I think that one had maybe 100 kilo electron volts capability. But the standard Ebits, they have electron beam energy up to 60 kilo electron volts. So yeah, you can create bare ions.
Yeah, it's quite impressive. Yeah, thank you.
Do we have more questions? I have a question of my own. I was when you showed that image of atomic number versus charge states. Yeah, that
Right.
one right there.
Right.
And you said that it is important that we figure out and fill up the entire map, right? Is it possible that when you go to higher atomic numbers, and you excite them to a charge state, that you end up getting a radioactive element or radioactive component?
Oh, you mean getting a radioactive component out of, I mean, if it's a radioactive isotope, you will, but if it's not radioactive in nature, if you're just working with stable atoms, then it shouldn't matter. You're not going to make it radioactive just by stripping their electrons.
Thank you. Do we have more questions?
Yeah, I was going to kind of go off what Dr. Chandra said. So like the protons and the neutrons are together and they're kept there together with the force of the electrons. But as you move the electrons away, wouldn't the stability of the nucleus deteriorate?
So you're removing the electrons, but your proton and neutron number is not going to change, right? So the strong force that's kind of like binding your nucleus together is still going to work in a similar way. But what we end up doing is that we end up going so much closer to the nucleus. So that's why we can look at the nucleus much more clearly now compared to like a neutral atom. You're just making it much more positively charged, but you are not really doing anything to the nucleus itself.
Okay, thank you.
So I have another question, which is, you mentioned you want to build an Ebit system here, right? So my first question is, how much space will that take? Because these instruments are huge.
They are not actually, and my goal is to be able to do the compact Ebits.
I see.
And if you look at the dimension here, the whole thing is 32 centimeter.
Oh, wow,
So
that's small.
of course you'll need, vacuum pumps and vacuum chambers and things like that, but the trap itself is going to be much smaller. And even with the conventional Ebits, they are not really that big. They are maybe a meter long.
And what elements are you going to look at?
To begin with, I'm interested in iron, just because of its astrophysical relevance.
Mhm.
And then, yeah, other astrophysical ones as well.
Okay, thank you. Do we have more questions for Dr. Silwal?
Yeah, I got another one actually.
Go ahead, Eric.
So could you remove a certain percentage of the electrons? Like how would you like control how many electrons you're going to lose?
Yeah, so that's where the electron beam energy comes into play. So basically, to remove each electron from the atom, you need a certain amount of energy. And it also depends on what element. So if you go to the NIST atomic database, and if you look at the ionization energy that you need to remove each and every electron, you'll notice that there's already a number for each number. For example, let's say you need 10 electron volts to remove the first electron, you'll need 20 electron volts to remove the second electron, and so on. So if I want to remove let's say 4 electrons out of the atom, then I have to apply at least the ionization energy to be able to remove those 4 electrons. And anything higher than that, like slightly higher than that, should be able to do that. And if we want to remove 40 now, then you have to apply much larger energy because you have to overcome the ionization energy of the 40 electrons. And yeah, that's exactly how you know.
Oh, that makes sense. Thank you.
Yeah, it is kind of difficult to create a very pure charge state. Like if you look at the spectra here, you see that you're not just seeing one charge state, you're seeing a combination of charge states. So in a way, it's difficult because these charge states have ionization energy so close to each other that a fluctuation of 5 eV or 10 eV can be sensitive enough that you'll be able to create a number of charge states. And the other thing that happens is there's also charge exchange going on in between the ions and the electrons. So whenever you're trying to create a higher charge state, what ends up happening is it collides with, let's say, gas or some other atom, and then it will take electron out of that, and then it will reduce in charge state. So that if you wanted to create a beryllium-like, you end up creating a lithium-like, and so on. So that's something that yeah, I struggle with, but as long as you can identify what everything is coming from, you can still you still have a full control over it.
For your experiments, what level of vacuum do you need?
So usually, typically inside we cannot measure right inside the trap, but right outside the trap, it's around 10 to the minus 10 millibar.
Wow,
So
it's ultra high vacuum.
yes, it's ultra high vacuum.
I was
And the trap
wondering-
down here, if you go to Dr. Calamai's lab, you'll notice that the vacuum there is also in the order of 10 to the minus 10.
Okay.
And it's usually easier the smaller the trap is, because there is less vacuum chamber to remove stuff out of from. The larger the system gets, the difficult it becomes.
Okay. Thank you.
Mhm.
Do we have more questions for Dr. Silwal? Students?
Looks like I gave too much information. But my intention was to blow people's mind.
I was wondering if the title of your talk, because you're talking about ions and you have the word Marvel there, has it anything to do with Captain Marvel from MCU?
No.
I was wondering if it is intentional.
It wasn't, but it could be.
Okay, if we have no more questions for Dr. Silva, let's thank the speaker once again for a wonderful talk. And this is the second last talk of the series in spring. We will have another talk next week. And that will conclude the series, the Colloquium series for this semester. Thank you, everybody, and have a wonderful weekend.
Thank you. Bye.
Thanks for the talk. Have a good one.